left off on page 7 of our Cornell notes, and as you can see here, we have a chart of the different materials that make up circuits. So just take a moment to read through the function of each of these and add the symbol to your chart. And all of these symbols can be located on page 4 of your reference table, so you do not need to have any of these memorized. On page 8, we have an example of what is called a series circuit. And a series circuit is just a circuit in which all parts are connected to end to provide a single path for current. So to keep our definition simple, we're going to say that a series circuit is just a single path for current. Now, all of these rules again are on page 4 for your circuit, so you do not need to have to memorize any of these rules. But it's very important to know that since there's only one current path in a series circuit, the current is the same no matter where we are. So whether we're in this resistor, or this resistor, the current is the same everywhere. The potential difference or voltage drop literally drops from one end of the resistor to the other, and those voltage drops have to add up to the total voltage of the battery. So the voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3 has to add up to 36 volts. And while our circuit is in series, it's very easy to just add up the resistors. As you can see here, we don't have to do anything crazy to add those, to just create a known and unknown chart to help you analyze the circuit. As you can see, we're given quite a few pieces of information here that are going to help us solve the problem. The first thing that we're going to do to analyze this problem is to solve for the equivalent resistance. And as defined, that would mean the single resistor that could replace all the resistors, and the circuit would still act the same. So we're going to take our rule for adding resistors in a series circuit, and we get Req equals R1 plus R2 plus R3. And now we can plug in with units and solve. So we get 4 ohms plus 6 ohms plus 8 ohms. And we add those up, we should get 18 ohms. And that's our Req. Now what that means, if we redraw this circuit, if we had a circuit that looked like this, draw my battery, it's 36 volts. If this resistor had a value of 18 ohms, it would act the same as this circuit. And again, just want to point out that we know this is a series circuit because if current flows, there's only one path for current to take. It cannot split. And when we get to parallel, part B, we want to find the current through each resistor. And like we just pointed out previously, since it's a series circuit, there's one path for current to take. Current is the same everywhere. I'll say it again, it's very important. In a series circuit, current is the same no matter we're here, we're here, we're here. No matter where we are in that circuit, it is always the same. And to calculate the current, we're going to use Ohm's law, which is R equals V over I. But it's very important when we're solving for the total current in the circuit, we want to use the equivalent resistance, which we found in part A to be 18 ohms. We know that the voltage of the battery is 36 volts, or the potential difference of the battery. You'll see some different vocab. And now we're solving for current. Rearrange, cross multiply, and we get 36 volts over 18 ohms. Do some division, and we should get that the current through this circuit is 2 amps. All right, now on to part C, where we want to find the potential drop across each resistor. And again, we need to keep in mind that this has to add up to this 36. So again, we're going to use Ohm's law, which is R equals V over I. And since we're looking for voltage here, I'm just going to rearrange it and have V equals I times R. First, I'm going to look at this resistor. And if we think back to part B, we know that the current everywhere is 2 amps. So when I'm talking about the voltage across resistor 1, we get 2 amps. Resistor 1 has a value of 4 ohms. Multiply this out, and we should get a voltage drop across R1 of 8 volts. I'm going to do the same for voltage 2, where now we have a 6 ohm resistor, so 2 amps times 6 ohms, and the voltage drop across V2 should be 12 volts. And finally, I'm going to do it a third time across resistor 3, which has a value of 8 ohms. Multiply that out, and I should get the voltage drop across V3 is 16 volts. Now, if we add up the 3 of them to double check our work using this formula, V1 plus V2 plus V3, I have 8 plus 12 plus 16, and by my math, that is equal to 36 volts. So that checks out, and I know that my work is done. Talking about finding the equivalent resistance of resistors in a parallel circuit, we have to use this formula, which is right off our reference table. 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. And I'll put a dot, dot, dot there, because if there were more like this, we would keep going. Now we're just going to simply plug in. I put our values here because they're not included in the notes. So now we would plug in. We get 1 over 4 ohms plus 1 over 6 ohms plus 1 over 12 ohms. I will share a helpful trick to do this very quickly in your calculator, but if not, we should find a common denominator, which is 12. And here we'll get 3 over 12 ohms plus 2 over 12 ohms plus 1 over 12 ohms. It's already 12. We would add all of those up, and we get 6 over 12 ohms. So then we find our equivalent resistance, or 1 over Req, to be equal to 2 ohms, which is very important. The thing that we're going to calculate is the potential difference across each resistor, which if we look at our rules, which again is on page 4 of your reference table, you'll see that V1, or V total, equals V1 equals V2 equals V3. And since our battery has a value of 12 volts, it is 12 volts everywhere in the circuit, which is now very helpful because we know it's 12 volts here, 12 volts here, and 12 volts here. So we can calculate the current at each specific resistor using Ohm's law, which is R equals V over I. Take the first one, for example. We have 4 ohms equals 12 volts over I. I'm going to set it up for the 3 different resistors. So for this one, I would get 3 amps of current, and that would be I1. Use a different color for I2. Where now the resistor 2 has a value of 6 ohms, still 12 volts because it's a parallel circuit. And we should get that I2 equals 2 amps. And we have to do this one more time for the third resistor. Where this has a value of 12 ohms. We still know the potential difference, 12 volts. And this is I3. So I3 has a value of 1 amp. What we're going to do is we're just going to check the entire circuit. So if we apply Ohm's law to the whole circuit, we use our equivalent resistance, which we found to be 2 ohms, the potential difference is 12 volts. And I should get a total current, so let's say I total, of doing the math, 6 amps. Now if I go back to what I did previously, we found 3 amps through I1, 2 amps through I2, and 1 amp through I3. And if we add those together, we get a total of 6 amps. So we know that we did our math correctly and both of those match, and we are good to go. We'll finish up page 10 in our Cornell notes, and we'll get ready to start practicing some example problems. As far as meters in the circuit, really the key thing to know is that a voltmeter is always connected in parallel. And an ammeter, which measures current, is always connected in series. And we want an ammeter connected in series because we want all of the current to go through. So we kind of want those to be right in the circuit. So here we can see that current splits. So this is going to be a voltmeter. Same with here. You can see these are measured in parallel, which means that all of the current goes through here, making it an ammeter. And same with this one. And then as far as conservation of charge in electric circuits, this point is what's called a junction in a circuit. And our rule for that is that the current in has to be equal to the current out. So if I make up some values here, let's say I have 7 amps coming in and I have 4 amps coming out. Well, I need a total of 7 amps coming out. Therefore, this would have to be equal to 3 amps.